The ground begins to tremble beneath the ancient settlement as a massive earthquake strikes the Anatolian plateau. Buildings sway violently. The earth cracks open, and debris rains down from collapsing structures. Yet when the shaking stops and the dust settles, one remarkable sight emerges. A cluster of stone houses built 9,000 years ago, still standing intact while modern concrete buildings around them lie in ruins. These prehistoric structures, constructed without a single piece of metal or modern engineering knowledge, have survived thousands of earthquakes that would destroy most contemporary buildings. How did our ancient ancestors create earthquake-proof architecture that puts modern engineering to shame? The relationship between humans and earthquakes is as old as civilization itself. Archaeological evidence shows that some of humanity's earlier settlements were built directly in earthquake zones, not because our ancestors were reckless, but because these geologically active regions often provided the most fertile soils, abundant water sources, and valuable mineral deposits. From the volcanic slopes of Mount Vesuvius to the fault lines of Turkey, early humans chose to build their homes in places where the earth itself was constantly moving. This choice forced our ancestors to become the world's first seismic engineers. They had to develop construction techniques that could withstand forces that modern engineers still struggle to understand. Without seismographs to measure ground motion, without computer models to simulate earthquake effects, without steel reinforcement or flexible joints, they relied on observation, experimentation, and hard-won wisdom passed down through generations of builders who lived through countless tremors. The archaeological record reveals that earthquake-resistant building techniques emerged independently in seismically active regions around the world. At Çatalhöyük in Turkey, dating to 7,400 BCE, researchers discovered evidence of construction methods specifically designed to handle ground motion. The famous stone houses of this Neolithic settlement show sophisticated understanding of seismic forces and ingenious solutions that would not be rediscovered until the 20th century. The key insight that ancient builders developed was that rigid structures don't survive earthquakes. Flexible ones do. This principle, now fundamental to modern seismic engineering, was discovered through bitter experience by prehistoric builders whose lives depended on creating structures that could move with the earth rather than fight against it. Archaeological evidence shows that they developed multiple techniques for creating flexible connections that allowed buildings to sway during earthquakes without collapse. At Jericho in Palestine, dating to 8,000 BCE, archaeologists uncovered evidence of the world's first base isolation systems. These early earthquake engineers had discovered that buildings could be protected from ground motion by placing them on foundations that absorbed and dissipated seismic energy. The technique involved creating layers of different materials, stones, sand, and organic matter that acted as shock absorbers between the building and the bedrock. The sophistication of these ancient base isolation systems rivals modern approaches. Analysis of foundation layers at Jericho shows that builders understood the importance of material properties in earthquake resistance. They used round river stones that could roll and shift during earthquakes, separated by layers of sand that provided damping. Organic materials like reeds and animal hair were woven into the foundation layers to provide tensile strength and flexibility. But the most remarkable discovery came from the excavation of wall construction techniques at sites across the seismically active eastern Mediterranean. Archaeologists found evidence of flexible joint systems that allowed stone walls to move independently during earthquakes. These weren't crude constructions, but sophisticated engineering solutions that required deep understanding of structural dynamics. The technique involved creating walls from multiple independent sections, each capable of moving slightly relative to its neighbors. The joints between sections were filled with materials that could compress and expand. Clay mixed with organic fibers, sand, and sometimes even animal fat. During an earthquake, these joints would flex and absorb energy, preventing the rigid stone walls from cracking under stress. Archaeological evidence from Göbekli Tepe in Turkey, dating to 9500 BCE, reveals even more sophisticated seismic engineering. The massive stone pillars of this ancient temple complex were designed with flexible connections that allowed them to sway during earthquakes. Analysis of the pillar bases shows that they were mounted on stone rockers that permitted controlled movement in all directions. The engineering behind these rocker systems was remarkably advanced. Each pillar base was carefully shaped to create a curved interface with the foundation, allowing the massive stones to tilt and return to vertical without toppling. The curvature was calculated to provide just enough flexibility to absorb earthquake motion while maintaining structural stability under normal conditions. Tool marks on the pillar bases show that achieving these precise curves required extraordinary skill and patience. Stonemasons used carefully controlled pecking and grinding techniques to create surfaces accurate to within millimeters. The work required not just craftsmanship, but sophisticated understanding of geometric principles and structural engineering. The shock absorption systems developed by ancient builders extended beyond individual buildings to entire settlement planning. At Kirokassia in Cyprus, dating to 7000 BCE, archaeologists discovered evidence of community-wide earthquake-resistant strategies. The settlement layout itself was designed to minimize earthquake damage through careful spacing of buildings and strategic placement of open areas. The street layout at Kirokassia follows principles that modern seismic planners would recognize. Buildings were spaced far enough apart to prevent collapsed debris from one structure from damaging neighbors. Open areas were positioned to provide evacuation routes and emergency gathering spaces. The overall settlement design created a resilient system where earthquake damage to individual buildings would uncompromise the entire community as survival. Building material selection was another crucial aspect of ancient earthquake engineering. Archaeological analysis shows that prehistoric builders in seismic zones developed sophisticated understanding of how different materials behaved during earthquakes. They learned to avoid materials that became brittle under stress and favored those that maintained flexibility and strength under dynamic loading. At sites like Hasala in Turkey, dating to 7000 BC, researchers found evidence of composite construction techniques that combined different materials to optimize earthquake resistance. Stone provided compressive strength for foundations and lower walls, while wood offered flexibility for upper structures and roofing. The interface between materials was carefully designed to transfer loads while accommodating differential movement during earthquakes. The wood selection process was particularly sophisticated. Archaeological evidence shows that builders chose specific tree species based on their seismic properties. Oak and other hardwoods were favored for structural elements because they maintained strength under repeated stress cycles. Softer woods like pine were used for non-structural elements, where flexibility was more important than strength. The joining techniques used to connect wooden elements were designed specifically for earthquake resistance. Traditional mortars and tenon joints were modified to include deliberate gaps that allowed for movement during seismic events. Wooden pins and wedges were designed to compress and expand, providing flexible connections that could absorb energy without failing. Archaeological experiments have demonstrated the effectiveness of these ancient joining techniques. Test structures built using prehistoric methods and materials have been subjected to simulated earthquake motion and performed remarkably well. The flexible joints designed by ancient builders often outperformed modern rigid connections in terms of energy absorption and structural survival. The roofing systems developed for earthquake-prone regions show particularly sophisticated engineering. At sites like Badr in Jordan, dating to 7000 BCE, archaeologists found evidence of roof designs that could flex and move during earthquakes without compromising the building's weather protection. The technique involved creating multiple independent roof sections that could shift relative to each other. These segmented roofing systems required careful engineering to maintain weather tightness, while allowing for seismic movement. Overlapping sections were designed to slide past each other during earthquakes while maintaining overlap for water protection. Flexible ceiling materials, made from tree resins and animal fats, were used to accommodate the movement, while preventing water infiltration. The maintenance requirements for earthquake-resistant buildings were significant and required ongoing community commitment. When you think of ancient builders, what comes to mind? Maybe the pyramids of Giza or the Colosseum in Rome. Massive, rigid structures built to stand for eternity. But what if I told you that in some of the most geologically active places on Earth, our ancestors pioneered a radically different approach? They didn't build to defy the ground's movement. They built to dance with it. This is the incredible, largely forgotten story of ancient earthquake engineering. Archaeologists digging through the ruins of ancient settlements and seismic hotspots have uncovered something amazing. These weren't just primitive huts. They were sophisticated structures designed with a deep understanding of how to survive violent shaking. And this wasn't a one-off stroke of genius. It was a systematic, community-wide effort that lasted for thousands of years. The secret wasn't in making buildings stronger in the way we might think, by making them more rigid. The secret was flexibility. Ancient builders understood that when the earth moves, A building that can sway and flex is far more likely to survive than one that stubbornly resists. This concept is at the heart of the most advanced modern seismic protection systems, yet our ancestors mastered it using little more than wood, stone, and rope. How did they do it? They developed ingenious, flexible joint systems. Instead of mortaring everything together into a solid block, they created connections that could move, absorbing and dissipating the immense energy of an earthquake. Think of it like the joints in your own body or knees and elbows allow you to move and absorb impacts. These ancient structures had their own kinds of knees and elbows, but building these structures was only half the battle. They required constant care. Evidence shows these communities supported specialized craftspeople whose full-time job was maintenance. They would regularly inspect the joints, replace worn-out flexible materials like ropes or wooden pegs, and ensure the foundation systems remained stable. It was a living architecture, constantly tended to and kept in a state of readiness. This knowledge was priceless, and losing it could mean the end of a whole community. So, they developed robust systems for passing it down. Master builders created specialized training programs, teaching apprentices the sacred arts of flexible construction. This wasn't just a job, it was a revered tradition, preserved with near-perfect accuracy from one generation to the next. The stakes were simply too high for mistakes. A single error in construction could lead to catastrophic collapse, not just of one building, but of an entire town. We know this knowledge was preserved so well because we see the same techniques pop up across vast distances and time periods. The exact same flexible joint designs and foundation principles appear in sites separated by hundreds of miles and even thousands of years. It's a testament to a highly effective, systematic transmission of life-saving information. Of course, their greatest teacher was the Earth itself. Every earthquake was a test, and sadly, sometimes a brutal one. But these ancient engineers learned from every failure. Archaeological sites show clear evidence of this learning process. After a major quake, you can see where buildings were reconstructed using improved techniques, specifically designed to address what had broken before. It was a continuous cycle of observation, failure, and refinement, a slow, empirical, but remarkably effective way to perfect their craft. Over centuries, this process led to incredible specialization. Builders in different regions developed unique solutions optimized for their local conditions. They used local materials and designed for the specific types of earthquakes common to their area. The builders in the Mediterranean faced different challenges than those in the Andes or in ancient Japan, and their architectural solutions reflected this deep, localized experience. So what happened to all this incredible knowledge? Why aren't we all living in flexible houses today? The decline began with the rise of larger, more centralized societies and new building materials. Rigid materials like fired bricks and concrete, combined with new construction methods, allowed for faster, more standardized building. In a world of rapid expansion, speed and scale began to take priority over seismic resilience. The time-consuming, craft-intensive methods of flexible construction were gradually abandoned and forgotten by the mainstream. But the knowledge wasn't completely lost. It survived in pockets, often among indigenous communities who continued to use their traditional building methods. And time again, when major earthquakes struck, a surprising pattern emerged. Modern, rigid buildings would crumble into dust, while nearby, traditional structures that incorporated these ancient flexible principles would still be standing, often with minimal damage. This astonishing performance has sparked a renaissance of interest in ancient engineering. Modern seismic engineers are now studying archaeological sites to rediscover these lost principles. Military engineers are adapting ancient techniques for building in earthquake-prone zones. And disaster relief organizations are incorporating traditional flexible construction methods into emergency shelter designs. These ancient ideas are providing powerful new solutions for the 21st century. One of the most remarkable things about these ancient buildings is how they performed in recent major earthquakes. At some archaeological sites, prehistoric structures have survived modern quakes with barely a scratch, while nearby contemporary buildings suffered catastrophic failure. It's the ultimate real-world validation of their ancestors' genius. Perhaps the most important lesson from all of this is that effective earthquake protection doesn't always require high-tech materials or complex computer calculations. The fundamental principles, flexibility, energy dissipation, and smart material selection are accessible to anyone. Ancient builders proved that with basic materials and a deep understanding of natural forces, you can create incredibly resilient structures. In their designs, earthquake resistance wasn't an add-on. It wasn't a separate system bolted on at the end. It was woven into the very fabric of the building, from the foundation to the roof. Every joint, every beam, every wall was designed with seismic performance in mind. This holistic approach created buildings that were inherently earthquake resistant. And believe it or not, it was cost. While the initial construction might have required more skilled labor, the long-term payoff was enormous. Communities that invested in these techniques enjoyed greater stability. They spent less time and fewer resources rebuilding after disasters, allowing them to thrive for centuries in places others couldn't. The story of ancient earthquake engineering is a profound testament to human ingenuity and our ability to adapt. Faced with a planet that refused to sit still, our ancestors didn't see an obstacle. They saw a puzzle to be solved. They became not just builders, but true seismic engineers, whose innovations and deep wisdom continue to inspire and protect us today. So, the next time you see a modern skyscraper sitting on massive rubber pads, isolated from the ground as shaking, remember where that idea came from. It came from those ancient builders who first discovered that the secret to surviving an earthquake was not to fight the Earth's power, but to learn how to dance with it. Their legacy lives on in our eternal quest to build safe homes on this beautiful, moving planet. Thanks for watching. If you found this journey into the past as fascinating as I did, please like this video and subscribe for more stories about the hidden genius of the ancient world. See you next time.